back, everyone. We're so glad to have you back at our Stern Innovation Conference this year, focusing on innovation and environmental sustainability. We had a terrific morning session, so many inspiring talks, and that can only be outdone by this afternoon where we have another terrific lineup. So I'm really excited. Right now, I get the honor of introducing Raphael Carty, who's an adjunct professor here at the NYU Stern School of Business. And Raphael teaches about commercializing disruptive technology and leading innovation with a curriculum that focuses on leading innovation in sustainable technology, smart buildings, and smart cities. He is the co-founder and CEO of Kalita Energy, which is a smart building solution startup that promotes sustainability and energy efficiency in commercial buildings. And without further ado, I'm going to hand it over to Professor Carty to introduce his panel.
Okay, welcome everyone to Innovations in Carbon Capture and Utilization. Let me just briefly go through the agenda and then introduce the panel. We've got two very exciting innovators here today. After introducing our panelists, I'm going to go through a brief overview of the carbon capture and utilization domain. Then we'll have our first presentation from CarbonQuest, followed by a brief fireside chat, then a presentation from Dioxycle, followed again by a fireside chat, and then on to audience Q&A open to all. So please think of your questions along the way so we can have a really good discussion. Basically, what we're looking at here, our panelists are both Brian Asparro, COO of CarbonQuest, which is a company applying point capture solution to the building environment, and David Wakerley, co-founder and CTO of Dioxycle, doing basically the transformation of the chemical industry using carbon utilization. Let me just give a very brief overview of the domain and just lay out the types of carbon capture, utilization, and storage, a brief historical context, as well as point towards new innovations in the space. Why is carbon capture, utilization, and storage so important? Four big reasons here. One is it's a way to capture emissions at the source in some of the hardest to abate industrial sectors: oil and gas, steel, chemicals, and others. These are sectors that disproportionately have been very hard to limit those emissions. This field is also an enabler of the least cost, low carbon hydrogen production needed for aviation, shipping, and trucking and other sectors in the green hydrogen revolution. This sector also provides a way to scale carbon removal from the atmosphere. As the window is closing to avoid the most onerous scenarios, we have opportunities with the technologies in this space as we cost reduce and get to scale on things like direct air capture to put carbon removal right alongside emissions reduction. And last, this opportunity to utilize carbon as a feedstock in all the different types of innovation and utilization is really unlocking radical new decarbonization pathways in a multitude of different industries. Let's just talk for a minute about how does carbon capture, utilization, and storage work. Up to the left, you can see that we're capturing carbon dioxide, whether it's from fossil or biomass-fueled power plants, industrial facilities, as I referenced a few moments ago, or directly from the air. Depending on the siting, that captured CO2 may be permanently sequestered right there in an underground area. But most often, the carbon dioxide is compressed into a liquid, transported, and then used elsewhere. And we'll get to the utilization in more detail in just a minute. Let me just do a quick definition of terms. Carbon capture and storage was the original umbrella term for this space. Today, it's often used mostly for the point source capture and storage, not so much from the atmosphere. Carbon capture, utilization, and storage is the new umbrella term, which reflects the increasing role of carbon utilization. It should encompass all tech in the space, but some people may still use it to refer more to the point source capture versus direct air capture. Direct air capture is a much newer innovation, just about 24 years ago, capturing diffuse carbon dioxide from the air. It's an emerging technology that's critical for carbon removal. Let's talk about innovation in the space. It might surprise you, but 90 years ago, the precursor to carbon capture and storage started when natural gas producers started to separate carbon dioxide from methane. Carbon dioxide in a solid form as dry ice for 90 years has been used as a refrigerant. It still is today. That's perhaps the first commercial carbon utilization market in America. As we fast forward to the 1960s, a new use emerged. The first pilot plant for enhanced oil recovery came from injecting carbon dioxide into oil wells to increase extraction. By the 1970s, that reached commercial scale. By the 1990s, carbon capture and storage moved from just extracting more fossil fuels to being seen as a way to really help with emissions reduction. And at the very end of that decade, in 1999, direct air capture was invented. Moving forward to 2010s, we had our first DAC pilot plant, and this is when carbon utilization innovation explodes, as we'll come to in a second. And in the last year, we've now achieved our first commercial scale DAC plant. Let's talk about point source to introduce Brian's talk. Original focus was on oil and gas fields. Today, it's a critical strategy and the DOE policy for reducing emissions in those hard to abate industries that I mentioned. But it's also being applied in non-traditional domains. And I think it's very interesting what CarbonQuest is doing in applying this to the built environment. Moving to carbon utilization, no matter where the source is from the center, on the right, we have the original utilization uses, starting with dry ice, then fertilizer, then additives to foods and beverages, or injecting it into oil wells. And all of these uses on the right, carbon dioxide is not converted. It's just taken either in a solid form as dry ice or a liquid and as an additive. As we move to the left, we get to some of the very exciting developments in the last 10 to 15 years. The conversion of carbon dioxide into fuels and chemicals, David will talk about that in a minute, or into building materials. It can be sequestered permanently by making it a component of cement and concrete. So carbon utilization today has gone far beyond fertilizers and putting the fizz in soda pop and enhanced oil recovery. Innovators such as Dioxycle are pioneering radical new decarbonization pathways by replacing petroleum derivatives with carbon-free alternatives using the carbon dioxide as the feedstock. So at this point, I'd like to turn the panel over to Brian, who would share his screen and talk about CarbonQuest. Thank you.
Fantastic. And thanks, Professor Carty. Appreciate the invite to speak in front of you all today. Nice to meet you all. I am Brian Asparro, the Chief Operating Officer for CarbonQuest. We're focused on reducing emissions in a large, broad built environment. The problem statement with which we're trying to solve here is reducing emissions in the built environment. And overall, emissions from buildings in the United States comprise about 40% of overall emissions. It's particularly an acute challenge within cities where buildings comprise 60 to 80% of emissions. In New York City, it's 67%, with transportation and waste being the remainder of the emissions. In particular, commercial, industrial, or C&I buildings across the United States utilize natural gas, primarily for heating, hot water, power, steam, and one of the biggest challenges to reduce emissions. As a matter of fact, in New York City, the largest single category of emissions, it comes from natural gas to heat buildings. And it's one problem that's very challenging to decarbonize. So from a journey standpoint with CarbonQuest, we really see two main trends as it relates to compelling building owners to reduce emissions. One being sustainability initiatives, net zero, scope 1, 2, and 3 initiatives that have been set primarily by property owners or corporations as a competitive advantage. Second, regulatory drivers. These regulatory drivers are primarily in the form of programs associated with capping emissions for large buildings and emitters. In particular, we're seeing this becoming more acute in cities. In the building sector, Professor Carty mentioned earlier, hard to abate, traditionally being focused on large industrial, from large heavy industry, steel, cement. What we're seeing in terms of hard to abate is large buildings being hard to abate. What does that mean? Essentially, the challenge or the cost to retrofit an existing building or property to reduce emissions or to change is cost prohibitive. And so we should be looking at those types of industries or buildings differently. We think, and what we're seeing is that is now going from cement and steel into large manufacturing, district steam to provide heat to a university or a number of buildings, food and beverage, hospitals, commercial properties, large residential properties. And so the definition of hard to abate over time has become very more broad and challenging for large building owners to reduce emissions. At the same time, 20% of emissions in the United States comes from natural gas in large buildings. We've calculated over 700,000 large buildings that fit that hard to abate definition. While, as we mentioned earlier, cities are on the path to implementing building performance standards. This is just a picture of a map across the United States, but over 1,500 cities in the United States have carbon reduction targets and will likely start implementing programs to cap emissions. New York City is one of the leaders in putting together programs to cap emissions. A program called Local Law 97 goes into effect in 2024 in a little over 2 months, where 50,000 of the largest buildings, all above 25,000 square feet, will have emissions capped and will be paying a penalty above that cap in the event that they emit above that said cap. Some of the pricing in the program with Local Law 97 is the highest really in the market at $268 per ton. It's estimated that by 2030, perhaps, and roughly 25,000 to 30,000 buildings will be subject to paying a penalty at almost an aggregate of $10 billion. And so this is becoming very meaningful for building owners to start to develop paths towards decarbonization, not just for sustainability, but also for looking at their own emissions and penalties that they may be facing. This is a picture, it's a busy slide, but it's actually from NYU. NYU has been very innovative in installing a 10 megawatt cogeneration or combined heat and power system right next to the Stern building, and supplies power, heat, and steam to 26 buildings on campus. And the challenge that building owners like NYU face with laws like this are penalties to be faced as a result of the emissions. At the time, when NYU installed the combined heat and power system, it was one of the lowest emission sources of power to be installed in terms of the efficiency associated with installing a combined heat power system. However, over time, with a focus on reducing emissions significantly and immediately, there's a challenge associated with a significant amount of natural gas on site that will be creating emissions. And this is where we, as CarbonQuest, really saw a great opportunity. What are buildings to do in terms of options for decarbonization? There's options of buying offsets, on-site renewables like solar, energy efficiency, electrifying fully the building or the property in order to receive low carbon electricity. What we're entering into the equation is what we're calling building carbon capture. As Professor Carty discussed before, traditionally this has been done at large industrial gas facilities and power generation, and we're taking it down to the building level. And we're doing so because we're seeing that in cases where property owners are looking to electrify, carbon capture can be 3 to 10 times cheaper for the same amount of carbon to be reduced. What is it? It's a technology that we've developed. It's a solution for natural gas emissions, which we call distributed carbon capture, a 4-step process where we extract out flue gas or the exhaust that otherwise would have gone out the chimney, which includes carbon dioxide. We separate the carbon dioxide from the nitrogen and oxygen through a materials-based approach. We convert that carbon dioxide gas to a liquid. It's beverage grade liquid carbon dioxide, and then we utilize it in applications. In particular, we're focused on utilization of the CO2 where it has a a benefit to the overall carbon economy in areas like concrete manufacturing. What this does is it reduces emissions for the building owner immediately, while also providing a valuable input into CO2 utilization. It looks like a system on site akin to a boiler system that gets located alongside. It's a skid-based design, can be located indoors or outdoors. The value proposition for building owners is that it's immediate decarbonization. It's cost effective. So what we're generally seeing on projects today are a 4 to 7 year payback. It's not disruptive to an operation as it's an add-on, and we're able to measure and report on the emissions that have been reduced. The picture on the right is a concrete block manufacturer in Brooklyn, where we're actually shipping CO2 from one of our first projects in Manhattan. They use the CO2 coming from a building effectively that was used to heat someone's grandmother's apartment. And we're taking that CO2 and putting it into a concrete block that then goes back your grandson's apartment building. And it's a lower carbon footprint than most CO2 that's produced on the market. It's recycled, it's competitive pricing, and it's local. We're shipping CO2 10 miles rather than hundreds of miles. And here's just an example of the technologies that are being built, including Dioxycle, where the CO2 is being utilized in many different ways. In this case, this is being used in concrete. It makes a profit. Earlier, I mentioned a 4 to 7 year payback. This slide shows a few different examples of a multifamily boiler property in New York City, to a district energy customer in Seattle, to a commercial office building in Chicago. The point actually is that across the broad, diverse set of buildings, this works very well and has a really good applicability to really meaningfully reduce emissions immediately. How we typically engage, we'll sell a project to a customer, and then we'll help them manage it over a 10 to 20 year basis in order to get the value, economically speaking, but also the carbon reductions that they can use for their sustainability or compliance reporting. We've now started to move into the market to offer what we call building carbon capture as a service, as a large part of the real estate market would either need or prefer a solution that can be an operating expense rather than a capital expense. Here's an example of one of our first projects at a multifamily property on the Upper West Side of Manhattan. It's been working for a year and a half, shipping CO2 to a concrete block manufacturer in Brooklyn. And we've just been able to show the fact that this has it's really one tool in the toolkit for decarbonization of the built environment. Lastly, I've been asked to talk a little bit about the innovation and S-curve journey. We formed the company a little over 4 years ago for what we felt was a great market opportunity. So we spent a lot of time in year one doing some early research and hired a bunch of smart people in the gas separation and systems development space. Year 2 and 3 were really built in our lab, building out the proof of concept, testing different types of technologies and approaches to something that we ultimately felt comfortable and achieved what we felt was valuable to the market in order to start scaling. And then year 4, we installed our first system, and this is really the early adopter phase. We've since sold and are starting to implement 5 more systems in New York City, and that's now starting to really take off, where we are going to start to focus on system integration, fast followers, and starting to build out further market and customer opportunities. So that's really all for the journey that we've been taking as CarbonQuest. And we're always looking for any ideas, customers, partners, or anyone that has interest in our journey. Please don't hesitate to reach out.
Thank you, Brian. I think, oh, Raphael is back. He had a momentary lapse of Wi-Fi, but I will turn it over to him.
Hi, thanks so much for that really informative presentation, Brian. I just wanted to ask you a few questions to tease out a little more about this innovation. It's interesting when an innovation is applied in a completely different domain. Carbon, as you mentioned, it's historically been used elsewhere. What sparked the idea to bring this point source capture and storage to buildings? It's the first, I believe, anywhere doing this. What sort of gave you the idea to bring it to this domain?
Great question. We believe this is the first of its kind in a building in the world. And it really came down to the market opportunity and the size and the veracity of the problem that we have as it relates to climate. And at the same time, we've built, at least in the United States, but this is really a global phenomenon, a lot of infrastructure around natural gas for heating, hot water, and for power. And the idea came, how do we do this as quickly and cost effectively as we can? We see things like renewable natural gas, hydrogen, all developing, but seeming to take a long time. How can we then take the core tenets of something like carbon capture done at large scale industrial facilities and take it down to a building level? And so that's really kind of what we looked at, Professor Carty, as the opportunity and the problem that was present. And that's why we really started the company. We also felt confident that we could build the technology and implement the technology around it based on our experience and our team as well.
Great, thanks for that information. And you also mentioned early stage, that market research and customer discovery to validate your approach. Let me just talk a little bit about, with any innovation, it's a great idea. A lot of the, going from that idea to actual installations as you've done is de-risking the technology to take that idea from the lab to a working on-premise installation. One thing that's interesting here is point source capture is a somewhat mature technology elsewhere in terms of technology readiness level, but this use case is brand new. So what's it like de-risking a technology that's somewhat mature, but in a completely new environment?
Yeah, the good in that example, or there is reference, there is technology around carbon capture in the broad market. There is commercially available equipment to utilize. So we didn't have to build brand new equipment, risky equipment. This is things like compressors and pumps and things that are commercially available in the market. And also the advantage here and the risk is that there really is a climate need. So it's really driving a lot of interest in the market that wasn't present 10 years ago, really. The bad, there actually references with carbon capture have been fairly challenging in terms of the perception of the value of carbon capture that we had to overcome. And also, why would you do this? Why would anybody put a carbon capture system in a building? No one's done it before. And so those sorts of perceptions are the things that we had to really think about and try to design around. And so in terms of de-risking the technology, traditionally carbon capture utilizes at a large scale a chemical, and it's called an amine. And so when we were designing this, we thought, geez, having a chemical in a building probably is going to be the best way to do this. So we did a lot of research, and we use in our technology a material. It's a manufactured material. For visual reference, it looks like a lentils, actually. And we felt that was the best way within the building environment that we could de-risk the technology such that there's no chemical, but it could be easily permitted and it would be safe, which is very critical. And in that case, de-risking the technology in terms of how the customer would look at it was really important.
Great. And just one last question. I met you several years ago and I was working on smart buildings before I was teaching. And from being in the space, I know that the real estate sector can be a little bit conservative on adoption of new technology. And, part of making an innovation successful To diffuse is to find customers to pilot, to get to those commercial deployments. Can you speak to how you were able to engage customers and get them to try something that was the first time ever done in their space in an industry that may be a little conservative on bringing in new technologies?
Great question. And one that I think every innovator tries to figure out as best they can. And so what was very helpful to our journey is the emphasis on the climate problem, but also New York City putting together a program that called Local Law 97, as we discussed, that really catalyzes the minds of property owners, especially, as you mentioned, conservative nature of real estate owners that typically really are very focused on net operating income as part of managing a property in order to keep it viable and manage their mortgages and whatnot. But penalties really impact that. So that net operating income has an additional cost potentially. So it drove a lot of interest, and that's why we started in New York. So from a market perspective, that was very helpful. Trying to get an early adopter is a challenge. Very rarely does someone raise their hand and say, yes, I'm an early adopter. Or some people may say I'm an early adopter, but they really aren't. And so how do you really determine who is and who isn't? So we spent a lot of time looking at different types of buildings and companies. And we just started going out and speaking to people. Is this a good idea? Do you find this interesting? Would you be interested in implementing something like this sooner rather than later? And once we found the property owner who said sooner rather than later, that's when we knew we had something there. And so we worked with them on what this would look like. We already had a prototype and the way we would look at this, but we also wanted to get their feedback so that we can get them comfortable. And I'll leave you on this because we've spent a lot of time with this is for within the early adopter phase, but even more broadly, we're trying to satisfy the economic buyer, the user buyer, and the technical buyer. In some cases, they could be all three. Usually they're not, but sometimes they can fill two roles. But it was important to really have that conversation about the economics and how this impacts the building, the technical side of impacting the building, and then what is the result here? Carbon reduction or compliance. And so that's where we ultimately believe we got them comfortable. And now we're doing the same with many others that are adopting the technology.
Brian, thank you so much for giving us insights to your innovation and your startup journey. And people have an opportunity to ask you more questions later. Right now, we're going to switch to David for Dioxycle and hear about their innovation. Hi, David. Welcome to the panel.
Hi, thank you. Really happy to be here. So it's a bit darker than I thought it would be. I'm in Europe right now, so we're on the other side of the world.
We can see you fine.
Give me 1 second. Great. Okay. Well, thank you, everyone. I'm just going to full screen mode. So it's really great to be here today to present to you Dioxycle. We are a carbon utilization company. We take renewable energy, carbon emissions, and our technology in order to produce sustainable chemicals, feedstocks, and fuels. And we're doing this at a time where our future clients, the industrial CO2 emitters, are facing some pretty strong tailwinds for decarbonization. So they're being offered increasing tax incentives, they're facing volatile fossil resource costs, and importantly, people like us are telling them they have to start using sustainable chemicals in their process. And this is where Dioxycle comes in. We make a carbon electrolyzer, which is able to take carbon emissions, renewable power, and re-energize those carbon molecules into sustainable feedstocks. In particular, we focus on ethylene. You may not really know much about ethylene, but it's definitely part of your life. It's the world's most used organic chemical. It has a market size of 170 billion per year. And it's really the Swiss Army knife of chemicals. So it's on the screen right now. I don't want to do too much high school chemistry, but this is a molecule of ethylene. And here are all the different things, not even close to what you can do with it. But on a very broad level, you can react ethylene with oxygen to make ethylene oxide, which is a precursor for a lot of liquid chemicals. You can react ethylene with chlorine in order to make vinyl chloride, which is a precursor for a huge number of different materials, such as things like PVC. And you can react ethylene with itself and make hydrocarbon fuels. And I won't go into how important those are, but you can imagine as well, this is something very valuable. And the really important thing for us as a company is we are providing these carbon emitters a technology that's able to give them a financial incentive to begin recycling their emissions. I'm a technical founder, so I'm going to go deep into how the technology works. The way this electrolyzer looks is that it's a series of plates all stacked on top of each other. These plates have specific grooves which allow carbon emissions to be transported from an emission stream to our central catalytic core. That catalytic core is comprised of 3 layers. The first layer on the bottom there converts carbon emissions into ethylene. There's then the central membrane that separates that first catalyst layer from a second catalyst layer, which converts water into oxygen. And I'm not going to go through exactly the chemistry here again, but the important thing is here we're taking carbon emissions and water, and we're using renewable energy to turn them into ethylene and oxygen. So it's really exactly the inverse of burning fossil fuels. And at Dioxycle in particular, we focus on optimizing this internal catalytic core. We focus on making the catalysts as efficient as possible, which lowers the power consumption of our process. And we work on maximizing our scale in order to have as large an impact as we possibly can. And just to show you the results of our development so far, we're just going to compare ourselves now to our competition. The incumbent technology for ethylene production is called steam cracking. It is a process where you take oil or gas and you just heat it like crazy. You heat it like crazy until the molecules break down and you make molecules of ethylene, and it's very carbon intense. So steam cracking produces around 1 to 1.7 tons of CO2 for every ton of ethylene that's produced. And every year that process generates around 260 million tons of CO2. On the other hand, if we look at our technology, our electrolyzer, we are taking those carbon emissions and actually converting them directly into ethylene. And at the same time, we're not doing any steam cracking. So overall, the potential carbon impact is around 3 to 4 tons of CO2 prevented for every ton of ethylene we produce. And at the same time, because our process is particularly efficient, we're actually able to produce that ethylene at about the same cost as the fossil alternative. And in some cases, we're actually able to undercut the fossil price. So the green premium, the extra cost of going green, which is often seen as a big barrier to adopting these new carbon utilization technologies, doesn't really affect us here. It's basically zero, and sometimes we even are able to offer a green discount. And we really believe that's key to getting our technology off the ground quickly and adopted at scale. And overall, this is our big picture perspective. We're looking to be able to decarbonize around, or I should say over 700 million tons of CO2 every year. So preventing them from being emitted either by not doing the steam cracking and at the same time by recycling those emissions. And so far, so good, I would say. And again, I was also asked to give you an idea of how we got this innovation off the ground. We're a little further down the S curve. You imagine that this graph is just on that very beginning part. We're 2.5 years in to the company. And this is just my depiction of our journey so far. So my co-founder, Sarah, and I, we were both technical founders. We were both working in Stanford and Cambridge and the Collège de France in Paris before we founded the company. We worked on the technology for a combined 10 years before jumping off this metaphorical cliff here to start the company. The beginning of the company was really just proving that the technology was real, it could work at scale, whilst also talking to customers, making sure we were making something that was really interesting to these industrial emitters. With all that confirmed, looking positive, we raised our pre-seed, which allowed us to basically repeat the same process, but at larger scale. So we validated the tech again at an even bigger scale. We validated commercial traction and then raised our Series A. And now we're in the process of making our industrial pilot reactor. So that's where we are right now. I finished up now just by quickly summarizing how Dioxycle in particular has managed the risks of this kind of innovative development, the development of a new innovative technology. And these are our 3 tenets. The first of which is just to build the best team. There's a photo of everyone there at our lab, not quite everyone. We have a lab in California too, but these are our Parisian chemists. This is a picture of them at the lab opening, which we're very happy occurred earlier this year. Our philosophy there is just to hire the best people, keep them happy. And second, we really focus our development. We make sure we set very clear goals. We make sure that we hit those targets. Basically, it's very simple. And finally, the last thing we've always tried to do as a company is to iterate quickly, because the faster you're iterating, the faster you're finding problems. There are always going to be problems, but the quicker you find them, the quicker you solve them. And that's it from me. Thank you for listening. I just summarized here where we are as a company, and I just wanted to shout out to our supporters. We had some incredible support early on from the Breakthrough Energy Fellows Program. And if you know anyone or you're looking to do any kind of climate tech venture, you should reach out to them to see if they can help. They're an incredible team. And we also have some incredible support from our Series A investors, Breakthrough Energy Ventures, Lower Carbon Capital, and Gigascale Capital, who are all phenomenal bunches of people. And that's it for me. Just one shameless plug. We are hiring. And if you're interested, please check us out on dioxycle.com.
David, thank you so much for this informative presentation about the genesis of your invention and where you are. A lot of great progress. I wanted to pick back up on one quick question on just what sort of sparked this idea to rethink chemical production using carbon dioxide emissions as your feedstock together with water and electrolysis to do a carbon-free solution versus the other way, which you mentioned was incredibly energy intensive. What was the spark of that innovation idea?
It's a big question. Honestly, there was no spark per se. If I'm really frank with you, we completely copied plants and trees. So
Wow.
we knew this technology was possible because plants and trees, they take CO2, they take energy, and they convert it into all of the different, biological products, but also they were the reason we have oil today. So all we're using is yesterday's plants and trees right now. So really that was what showed us that this was possible. That's our inspiration. And Sarah and I, we were both working in academia on the subject of mimicking photosynthesis. So we were trying to do the same reactions. We were working at Stanford when we were really having these thoughts about forming a company. And during that time, we really had the genesis of Dioxycle, let's say. We really had that moment where we had some, there were wildfires, there was clear climate change, and we had some existential dread. We had to leave our academic jobs, just take the splash and begin working on scaling up this CO2 conversion tech. And it's really the driver for us to try and beat the fossil alternatives is just because we have to, as a species.
Now, I love the fact that you're using biological models and applying that to this problem. It's really it's a great inspiration. One thing you're doing is, you've achieved tremendous efficiency in your process. That's part, as we've discussed before, it's part of really achieving this great performance. How did you establish those initial targets and track it and then sort of measure your progress to attaining it? Was there a significant sort of modeling and simulation and optimization that helped you guide that effort to reach these really breakthrough results?
Definitely. So we very early on, we were building techno-economic models and also process models. So we were modeling the process, we were modeling the techno-economics. We have some incredible talents on the team who are experts on that modeling. And through all the extra values, all the different constants involved, I won't go into it in detail, but the main thing for us is we have the price of electricity and we have how much electricity we need to convert, let's say, 1 ton of emissions into 1 ton, or some tonnage of emissions into 1 ton of ethylene, I should say. And then it's just a factor of looking at how efficient we can make our process versus how we predict the energy price will change over time. And so for us, we just pull those 2 levers. We make sure we're very conservative with where we think the energy, the price of electricity is going to go, and make sure we're very ambitious with what we think our technology will be able to achieve. And by ambitious, I mean in our development, not setting ourselves wild targets, but just making sure that we're setting ourselves targets we can achieve that are pushing the boundaries of efficiency. And then, if I'm frank with you, we just get to work. We just get in the lab and make it happen. And that's really why it's so important to have a passionate and talented team.
Fantastic. One last question. I love your green discount approach as opposed to asking customers to pay a green premium to buy a sustainable alternative. Did you start with being cheaper than conventional as your initial design goal, or did you find that you were able to meet and then beat the status quo as you continue that efficiency optimization that you've already described?
Right, great question. So obviously it was our dream, everyone's dream, to undercut the fossil price, right? There would be no issue with climate change if green chemicals were cheaper than the fossil alternative. We didn't set off with that goal. What we did was we made sure we targeted a chemical, so ethylene, which would be very robust to green premiums. So you can imagine for ethylene, if you tell someone they're going to have to pay 50% more for ethylene, there was still going to be a market for things like clothing. People will pay more for clothes if they know they come from sustainable sources compared to things like gasoline. The gasoline, if you do CO2 to gasoline, you really have to be working at low green premiums to get that off the ground. So we were working with ethylene, which we knew would be relatively tolerant. We'd have some markets to begin with it once we made our green ethylene. And then honestly, no, just year and a half, 2 years into development, Sarah was working on a techno-economic model and just came back and said, hey, our green premium is negative. Obviously, we checked a few times and it was definitely negative. And we told our investors, hey, we're at the point now where we think we're selling for under the price of fossil ethylene. We were going to call it negative green premium. And that's when they sent us an email across and said, hey, a negative premium, that's a discount. And we're like, oh yeah, no, it's a discount. And honestly, we didn't plan for it. We're very happy to be there. And now it's just that green discount, it really applies to a concerted effort. The technology will obviously have to grow. There's economies of scale, as well as a global installation of more power that can help bring down the electricity price, not by much, by just a little bit, to get that green discount.
Fantastic. I hope other industries and other companies adopt that approach and just shift it from a premium to a discount. We are now, thank you so much for answering those questions. We're coming to the end of the session, but I wanted to open this up to either David or Brian if we have a question from the audience. I'm looking in the Q&A right now and I don't see it, but if there is a question out there, we have time for one question on either of these presentations, if somebody wants to put it in the Q&A.
Or we could encourage Brian and David to talk to each other as well. That would be interesting.
Definitely. What questions do you guys have for each other? Very divergent innovations here.
How much CO2 can you get us?
Well, there's just in the United States alone, there's a 1.5 billion tons. So we'll ship it your way.
Thank you. Yeah. We'll build a pipeline. So on a more serious note, what's the kind of price you're targeting? Do you have a price you can say you're targeting for every ton of CO2, let's say, you're selling?
So in terms of production, we're on a CapEx basis about $100 per ton today, going down 30 to 50% in the next 3 to 5 years. So it'll be about $50 a ton or so. And these are smaller systems. Because we're also offsetting a potential penalty, $268 per ton. The United States also has a federal tax credit called 45Q. It allows us to sell CO2 at a relatively low price, anywhere between $50 a ton going up to a few $100s a ton, depending upon the market where you're located. Is that getting CO2 or how you get CO2, is that an important consideration in what you're doing in your process?
Obviously, it factors into the model, and the purer the better. We do have some tolerance to impurities, but when we start working out exactly how much the carbon emission is going to cost, we need to be sure that it's affordable, because otherwise it starts eating into the price of the ethylene or the sale price of the ethylene. So the cheaper the better, basically, and technologies like yours are really key to getting there.
Well, I'd just like to thank you both. We're at time now. David and Brian, incredibly insightful presentations on some of the leading edge innovations in the space. Keep doing the great work you're doing. It's so much of a big help in the climate change initiatives. Thank you much. And that's it for us. Turning over to Melissa. Thank you.
And
Thank
thank
you.
you, Professor Carty. It was a terrific talk. Thank you to Brian, David, just fascinating. And I hope you guys are wildly successful because it gives me hope that our planet will actually survive. So keep working, guys. Thank you.